I given A, B, C. I want to simplify this. A, this is M, this is N. B, C, B is M by R, so this is M, so this is R, okay. B, okay, and then R by N. So this is shorter, so shorter. This is N, so same as this, so something like this. So C, this is R, this is N. So that these two multiplied together should give me this. I want to subtract them because they have the same dimension, so of course I can subtract them. Okay, so this is the whole thing. I want to expand this. So what is this? You can think of this as how much mismatch between B, C, and A. Suppose A equal to B, C, then subtraction is 0. So this guy is 0. So what I'm talking about is, it's like this is the amount of error between A and B, C. A is a matrix, B is a matrix, C is a matrix. So I'm saying, I write down a matrix as a product of two matrices. Suppose M is 100. So I have 100 row, okay? And let's say N is 1000. This guy have 10 to the power 2 times 10 to the power 3, so 10 to the power 5 number of things. Let's say R is 3. Then I have how many? 100 because 100 by 3. So this has 300 things. This will be what? 3000. So I have what? 300 times 3000, much smaller than this number. So you can also think of it as a compression. So I'm actually using a few stuff to compress this a bunch of numbers. This is possible if this matrix is low rank. Before we achieve this factorization, that means I write A as BC. I need to first know how to measure this. So this is the thing. Recap vector V. If you draw it in two-dimensional plane, this is x coordinate, this is y coordinate. You know AB is just something like this, right? The x coordinate is A and the y coordinate is B. Pythagoras theorem. What is the length of this vector? A squared plus B squared square root. So this thing, we call it the norm of V. This is the same as I have a vector component 1, take the square, and I have a vector component 2, I take the square. Write this, right? Basically, this is my V1, this is my V2. This is the same as well. I don't write each of them, I write summation sign. All the component index I, Vi squared. So this is the idea. What is Euclidean norm? You take every stuff inside, take square, sum all of them, take square root. With the same argument, what is this? Same idea, right? Now this A have two index Ij. It's the same. I just have two index Ij and all the Aij take square. So it's the same as this. It will be just, okay? So this is the same thing as a vector. Important. For vector, we write a 2 here. For matrix, we don't write a 2. We write an F. F stands for forbiddenness. It's a person's name. Now I'm going to tell you a funny fact. A forbiddenness norm is the same as trace of A transpose A square root. Why this is true? What is A transpose A? This multiply this, it will be. Okay. I don't care. Why? Because I have trace. Trace only give you diagonal, so you only care about these two. A square plus C square plus B square plus D square. Okay, now you see I F norm have a square root. So if I put a square root here, I have a square root here. This thing is this thing. Therefore, forbiddenness norm of a matrix is the trace of A transpose A square root. Then this one, starting point. So now we can start. By definition of this, I just show that forbiddenness norm of a matrix A, red thing, it just trace the red thing transpose times itself. So I just have this. Then I just look at this guy. This is this guy. Then distributed. So I have this and this. I just put the transpose inside, okay? Now transpose xy is same as ytxt. Then this red part, because of this red thing, become this red part. So now this thing, I expand, okay? This A multiply this A give me this term. And then this A multiply BC give me ABC with a T. And then this negative B times A give me this negative B thing. And lastly, negative and negative give me positive, okay? So I have this big chunk of thing. All these are equal. So this big chunk of thing equal this big chunk of thing. This big chunk of thing, trace can go inside. I can go to here. So I have this. Be careful of the signs. So we have negative here. This is negative, this is negative, this is plus, so this is plus. And then A transpose A trace is just norm. So this thing become norm. So now I have this thing. Trace is cyclic invariant. Trace AB is the same as trace BA. So I'm going to do on this part. I'm going to move the C to the front. So this in the back, move to the front. I have this. So now I have this thing. So A minus BC for base norm square equal to norm of A minus this big chunk of thing. Trace D is D transpose because under transpose. Diagonal don't change, right? Only the off diagonal change. So this thing is same. I put a transpose on the whole stuff. Then by this XY bracket T is YTXT. Now I have what? My X is this thing. My Y is BC. So I do the same stuff here. I get this. And then this I reuse the XYT again, I get this. So A transpose BC give me this, and I have this term and this term. What I show is that these two terms are the same thing. So now I have a 2 here. Now I have this 2. And then again, I'm going to use cyclic invariant again. I can move the C to here, so I have a B in the end. So I have this big term. This one is trace A transpose A square root. Now I'm going to tell you, if I have A inner product B, if I have a vector U and V, so U is like AB, V is like EF, then U dot product V is what? AEBF. So this is the same as what? Summation UI VI thing, right? Then what about matrix? Aij, Bij. Forbiddenness norm is like this. Now, inner product between matrix C, it will be the same thing. Okay, so trace of A transpose B is the inner product for matrix between AB. Therefore, rewrite this thing into inner product. First, this whole line is this whole line. Then what? So first look at this term. I have this because I put the C in the back because this is invariant, cyclic invariant. I can do that. And then this blue part is the same as I do this, right? Now, the first guy with a trace will be the first term here. So this thing is the first term here. The second guy after the transpose is here, okay? So now this term is this term. Under the same argument, I can get CC transpose BB. This is a C and this is a C. Here, I can do the other way around. I write here is a B and this term is the same. I now have this. If our focus is on B, is this, which is equivalent to this inner product minus 2, this inner product plus the constant. What's the constant C here? It's just A norm, okay? So C is A norm, Q is CC transpose, P is AC transpose. So I have this thing. Now, if our focus is on C, then I just do the same thing. So I have this, P is AB transpose A, and C is the same thing. So that means this expression is the same as this expression. This expression is the same as this expression. So that means I have now, what? Throw away all the stuff that is not B in this expression. And same, for all the stuff that is not C, I write it here. I throw away, I don't care. So what I'm doing is that the minimization problem, suppose I want to minimize this thing. What's this? The product BC should give me A. I want the error to be as small as possible. And now I have two variables, B and C. Suppose I only care about B, then I want to minimize this on B. Then because they are equal, they are all equal sign. So that means minimize FB is the same as minimize this bunch of thing, which is this thing, where the Q and P are written here. The whole derivation is just basically these 5 pages. Is to tell you how do you get this, okay? Similarly, if I want to minimize this thing on C, because of this line, minimizing FC basically means minimizing this with respect to C. I get this big chunk of thing, so it's the same as I minimize this thing. And notice, I don't write the plus small c here. Why? Because it's a constant, so I don't need to care about constant.